Well, hello, everybody. This week we're talking about T-Test. The T-Test is going to be your first introduction to performing a real statistical test and trying to understand this whole matter of significance from an applied point of view. So go back to the worksheet that you did for last week and all those terms I had you look up in terms of hypothesis, significance, all of those areas. Remember those because you're going to need to understand those to be able to calculate and make meaning out of the t-test for our assignment this week. So exactly what is hypothesis testing? Because that's what we're going to be doing when we calculate a t-test. All significant tests require that you specify a test statistic to measure the effect you're interested in and help you determine whether that observed effect lies within the range of normal chance variation. Now, that's quite a mouthful to say, but basically, hypothesis testing requires that we choose a statistic, and this one's going to be the t-test, to measure the difference in what we observe. Our observed values, our observed effect is our raw data. So when we just look at our raw data, like we did when we did our descriptive information about our sample, so like when we looked at our the work-life scale, and you guys broke that down into who had good, bad, very good levels of work-life balance based on their job category, administrators, clerks. Those are our observed, that is our observed data. That's what we observe. Those are our raw numbers. But when administrators have a lower work-life balance than cooks, is that real? Is that data real? Or did it just happen by chance? That's what we're trying to determine. Because in our example, our hypothetical example we're using in class, if it's real, if administrators really have a lower work-life score and balance than cooks, then we could go back and look, do we have a higher turnover in administrators? And then we could dig deeper to find out why they have a lower quality of work-life balance based on some other variables, and then we could provide some interventions so that we could then reduce our turnover rate for administrators. So when we look at our data, we want to know, is it real? Is what we're looking at real? Or did this kind of happen by chance? And that's where our statistical tests come into play. So in our class example this week, you're going to examine if bullying awareness differs between girls and boys in first grade. So what we want to know is we're looking to maybe create an intervention to raise bullying awareness. And some of our research that we did to establish our study tells us that maybe girls have a higher level of bullying awareness than boys do. So before we design an intervention, we want to know if the girls in the first grade classes that we're going to be designing the intervention for have a higher level of bullying awareness. Because if they do, in fact, then maybe we can actually incorporate them a little bit more into the intervention to help the boys understand and have a greater awareness. So that could be our justification for trying to determine if there's a difference in the level of bullying awareness and the impact bullying has between the genders. That's the example. That's the class example you're going to do this week in your, and it's presented in the other two videos. Some of the theoretical aspects of statistical testing is in the statistical significance has to do with the error. So in assessing statistical significance, and remember, we use the term statistical significance in research to mean that there's a real meaning behind the data. It didn't happen by chance. So there's two types of possible errors. Type 1 error is when we mistakenly conclude an effect is real when it was really due by chance. So if we were to mistakenly conclude in our class example that the girls had more awareness than the boys, and we created an intervention and brought the girls into it to teach the boys, and we were wrong, then our intervention might not be successful. So we took the chance. We're going to talk about significance level, which is the 0.05 value, but we mistakenly concluded in our interpretation of our results that our observed data was real and that it didn't happen by chance. A type 2 error is in which we mistakenly conclude that that an effect is not real. We say it was due by chance. So in our class example, if we looked at our observed data and we calculated the t statistic and we interpreted it to say that the girls did not really have a greater awareness about the impacts of bullying, and so we created an intervention that was equal for both boys and girls, when really the girls did have a greater awareness. They could either be bored, tune us out, not get anything out of the intervention. It wouldn't change their level of knowledge, which is what we're trying to do. So we could make a type 2 error. We use the p-value, and the p-value as a point of information to determine if an effect is by chance or if it's real. The p-value is an alpha value, and we set it ahead of time. And in social sciences, I know you've heard this many times, we set it at 0.05. And what we're saying is we're willing to take the chance 5 times out of 100 to commit either a type 1 or type 2 error. So we're giving ourselves some leeways there that we're going to be able to interpret our statistical test at a level where only 5 times out of 100 would we be wrong in saying there was an actual real difference or there wasn't. So that's what the p-value is. The p-value refers to that alpha value that's set before you begin your statistical testing. In behavioral sciences, it's almost always 100% set at 0.05. Like I said, we're beginning with the t-test. This is the first inferential test you're going to calculate. And a t-test is a type of inferential statistic that's used to determine if there's a significant difference between the mean of 2 groups. That's the independent samples t-test. A t-test is used as a hypothesis testing tool which allows testing of an assumption applicable to a population. So again, we're testing a hypothesis, so we'll have to have a hypothesis about the data or the relationship that we're testing. Like we said, maybe we did a literature review, we looked at the research. Girls in first grade tend to have a higher level of bullying awareness, so we're going to hypothesize that in our classrooms, the girls have a higher level of bullying awareness. So calculating the t-statistics requires 3 key data values, okay? Number 1, the difference between the mean values from each data set, and that's called the mean difference. So therefore, because it requires the mean value, which we know is an average, then we know that we have to have data at a level that is interval ratio. It requires the standard deviation of each group. We know we get that when we calculate our descriptive statistics. We get the mean, we get the standard deviation, and the number of data values of each group. So however many is actually in your group, however many data values was gathered. Now, fortunately, you don't have to do the formula yourself. Excel captures and computes all that information, and you don't have to do these calculations by hand. But these are the 3 key components that you need to calculate the formula for the t-test. And again, the issue with this is that mean and standard deviation, because that tells you that you have to have, you can only calculate a t-test if you have variables that are at that interval ratio level. There's basically 2 types of t-tests that we use in social work when we're doing our evaluations of our programs or practice. The t-test for independent samples is used when we're interested in finding out if there's a difference on mean scores of one or more variables between two independent groups. Independent groups means the two groups are not related in any way. Each participant in the study is tested only once. So in our first classroom example, we're actually determining the difference in knowledge about bullying awareness between boys and girls. Boys and girls are our two independent groups, and we're testing them on their knowledge of bullying awareness. So we're testing them only once. So that's the t-test for independent samples. The t-test for dependent samples, or what's called a paired samples t-test, is when a single group of the same subjects is being studied under two conditions. Now, most often, and it's just rare that you don't find it's not under these conditions, but most often it's when we do conditions before an intervention and we administer a pre-test, and then after an intervention and we administer a post-test to determine if there's a significant difference in the means from pre-intervention to post-intervention. So we have one group of participants and we're measuring them at two different points in time. That's the paired samples t-test. Independent samples is two independent groups measured on the same measure, and we're comparing the difference. Paired samples t-test is one group or one sample, and we're comparing them at two different points in time, and then we're looking at the differences in the mean scores for the two different points in time. So if you just think about the paired samples as being a pre-test, post-test, and then the independent t-test as being a minimum of two groups compared on one test, to help know which one to calculate when you need to do your hypothesis testing. Now, when you get to your Excel, this is what the sample output is going to look like. And again, I walk you through the Excel in the next two videos, but this is what the sample output is going to look like. So you actually get the means here, and you have 5.43 for the boys, 5.53 for the girls. You're going to run your descriptive statistics first, just because that's what we always do. And when you run that descriptive statistics, you also get the standard deviation, which you need to report in your findings. But this right here is actually the t-test to sample, which is the independent samples. And it does give you the mean in the output. So here you have degrees of freedom. The degrees of freedom is a value that's different for different statistical tests, and it approximates the sample size of a number of individual cells in an experimental design. Again, this is part of the formula for inferential statistics, and basically it's n minus 1. So if you actually have 59 participants and you take away 1, you're going to get degrees of freedom for 58. In this case, because it's two samples, so we have 60 participants, we have 30 boys and 30 girls, so we have 2, so it's n minus 2, and that gives us degrees of freedom of 58. Again, you don't have to know how to calculate that because Excel calculates that for you, but when you write your results, you report the degrees of freedom. Then you have the t-stat, which is the t-statistic. For this one, it's a negative 0.14. The t-statistic represents the t-distribution. Again, you don't have to understand everything behind this, but you have to know how to pick out the t-statistic in this output because you have to put that into your writing of your results. So these are the things I've highlighted here are the things that you're going to need to know to be able to write your results. And because we're hypothesis testing, And we have to know the difference between a one-tail or a two-tail hypothesis. Did we write a directional hypothesis or a non-directional hypothesis? We have to know that ahead of time, because when we run our statistics, we get both outputs. We get it for the one-tail and we get it for the two-tail. Because we hypothesized in our example that girls in first grade would have a higher level of bullying awareness. So it's a directional. We're saying that the girls are going to have higher level, then it's a one-tail, and that's the p-value we select. If, in fact, we had just said there would be a difference in knowledge of bullying awareness between boys and girls, but we didn't specify which group would have a higher or lower level, we just said there would be a difference, that would be considered a two-tail hypothesis, and we would choose that particular p-value in our interpretation. So you have to know your hypothesis ahead of time, if it's a one-tail or a two-tail, because when you get to the output, you have to know which p-value to choose to make sense out of your data and determine if it's real or if it happened by chance. And this is how you would write your results for the particular example, and this is the class example. So you'll see as you move through that class example that this is how you're going to write your results for your independent samples t-test. And at the very top, I wrote the statistical way that you write the formula. This is the accepted way to write the formula for a t-test. You can see you have your degrees of freedom in the parentheses, and then you have the equals, and then you have your t-stat, and then you have your p-value, which was over 0.05 because it was way higher than 0.05. So there's an independent samples t-test was calculated comparing the mean score of first grade girls on a bullying awareness scale to the mean score of boys. No significant difference was found, and then you put your statistical information in right there to show the reader what the statistical information was. The mean score for bullying awareness scale for the girls, which was the mean of 5.53, a standard deviation of 3.42. We got the standard deviation because we actually calculated descriptive statistics before we calculated the t-statistics, was not significantly different from the mean score on the bullying awareness scale for the boys. The mean was 5.43, standard deviation 2.06. That is exactly how you would write your results. That's it right there. Nothing else beyond that. But you have to pull out those key numbers out of your output to be able to write your statistical reference in there. So that's a brief breakdown of the t-test, the key components you need to understand to be able to calculate a t-test for data. There's lots of theoretical assumptions behind the t-test, but this is the key information you need to understand to be able to calculate a t-test, whether it be independent samples or a paired samples. Pull out the significant information from the output and make a determination: is your observed values real? Is there a real difference in your observed values, or did it happen by chance? That's what we're trying to determine when we calculate inferential statistics.